Hello everyone, welcome back to Cloud Pathway Academy. If you're learning AWS and want to move beyond just memorizing services and actually understand how real-world production systems are designed, then this video is going to be a complete game changer for you. Today I'm going to teach you how to design a highly available architecture on AWS, what that means, why it matters, and exactly how the pieces fit together. Let's get into it. Imagine your app goes down at 2 a.m. on a Friday night. Your users cannot log in, your team is scrambling, and you're losing revenue every minute. Today I will show you how to design a system where the situation simply cannot happen. What is high availability? Let's discuss the basics. What does high availability actually mean to you? High availability, or HA, means your application stays up and running even when individual components fail. Now here is the important thing to internalize. In any real system, failures are not exceptional events. They are normal. Servers crash, network experiences latency spikes, hard drives fail. These things happen, it's just a matter of when. The question is, when something fails, does your system go down with it? High availability is the engineering discipline that ensures the answer is no. The formal definition you will see in AWS documentation is uptime measured as a percentage. 99.9%, 99.99%, or even 99.999%, often called 5 nines. The central principle here: eliminate every single point of failure in your architecture. Now let's understand why traditional setup fails, and they do fail often at the worst possible moments. Imagine a classic setup. You have a single server hosting your entire application. All your users connect to that one machine. Everything works beautifully until it does not. That server's hard drive fails, or it runs out of memory under peak load, or a routine OS update goes wrong. What happens? Your entire application goes down. Every single user gets an error, and it stays down until your team can manually diagnose and fix the issue, which can take minutes, hours, or even longer. This is not a hypothetical situation. This is how majority of traditional on-premises and early web systems operated, and it is exactly why downtime was so common and so costly. There are three fundamental problems with this model. First, there is no redundancy. One server means one point of failure. Second, there is no automatic recovery. A human has to intervene. And third, there is no scalability. One server can only handle so much traffic before it buckles. AWS was specifically built to solve all of these problems. Let us see how. Before we design our architecture, now we need to understand the infrastructure we are building on. And this is one of AWS' greatest competitive strengths. AWS organizes its infrastructure around two key concepts: regions and availability zones. A region is a geographical area where AWS has deployed infrastructure. For example, AP South 1 is the Mumbai region. AWS is currently over 30 regions worldwide, with more coming. Inside each region, there are multiple availability zones, typically 3 or more. Think of each availability zone as a cluster of one or more physical data centers, each with its own independent power supply, cooling, and networking. Here is the critical insight. Availability zones within a region are physically separated, far enough that a localized disaster like flood or power outage affecting one AZ does not affect the others, but they remain connected via high bandwidth, low latency fiber links. So your application can treat them almost like a single environment. The physical isolation is structural foundation of high availability on AWS. By distributing your resources across multiple AZs, you get redundancy built into the geography itself. Think of AZs like separate buildings in the same city. If one building has fire, the others keep running, but they are all connected by a fast private network, so your application, they feel like they are in one place. Now let's put it all together and design a highly available architecture. Look at the diagram on screen. I want you to understand every layer of this because this is an architecture pattern you will see in almost every production AWS environment. At the top we have our users. people accessing your application from anywhere in the world. The request first hit the application load balancer. The load balancer is the intelligent entry point for your application. It receives all the incoming traffic and routes it appropriately. We will go deeper on this in a moment. The load balancer distributes the traffic to EC2 instances, your application servers. And here is the key design decision. These EC2 instances are deployed across two availability zones. We will refer them as AZ1 and AZ2. So if your AZ1 experiences a failure and those EC2s goes offline, the load balancer immediately stops sending traffic and routes everything to the healthy EC2 instances in the other availability zone, which is AZ2. Your users experiences zero downtime. At the data layer, we use Amazon RDS with multi-AZ enabled. You have a primary database in AZ1 and a standby replica of the database in AZ2, continuously synchronized. If the primary fails, AWS automatically promotes the standby. This architecture eliminates single point of failure at every layer, compute, routing, as well as data. This is what makes it a production-grade architecture. Now let's zoom into the application load balancer, or what we call the ALB. The ALB sits in front of your applications and serves as a single entry point for all users. Users never connect directly to your EC2 instances. They connect to the load balancer, which then decides where to send the traffic. It does this in three important ways. First, traffic distribution. The ALB routes requests evenly across all the healthy EC2 instances using algorithms like round robin. Second, health checks. The ALB is constantly pinging your EC2 instances, by default every 30 seconds, asking, "Are you healthy?" If an instance fails to respond, the ALB marks it as unhealthy and stops sending traffic. Automatically, no human intervention is required. Third, the ALB itself is a managed, highly available service. AWS runs it across multiple AZs under the hood, so it is not a single point of failure in your architecture. From your user's perspective, the application simply works. They never see a failed server. The load balancer handles that invisibly. Now let's talk about auto-scaling group. This is one of those AWS features that genuinely changes how you think about infrastructure. An auto-scaling group manages a fleet of EC2 instances. You define a number, let's say 2 instances, and a minimum of 2 and a maximum of 6. AWS keeps your fleet within those bounds and automatically adjusts based on demand. Here is how it works in practice. Let's say your application normally runs fine on 2 EC2 instances, but then your product goes viral and you run a promotional campaign and traffic suddenly triples. Without auto-scaling, your 2 servers are overwhelmed. Response time spikes, user experiences errors, and potentially it might lead to the server crash. This is the classic example of a traffic spike. With auto-scaling, as CPU utilization on request crosses your defined threshold, let's say 70% CPU, AWS automatically launches another EC2 instances within minutes. Traffic gets distributed to the newly launched EC2 instances. The system remains stable. And when the traffic normalizes, auto-scaling scales back in, terminating the extra instances which we have launched when the traffic spiked. This means you only pay for what you use. High availability does not mean running maximum capacity 24/7. Autoscaling also integrates directly with the load balancer. As the new instances are launched and pass health checks, they are automatically registered and begin receiving traffic. Now let's talk about the database layer. And this is arguably the most critical piece to get right, because database failures are often the most damaging. AWS offers RDS, which stands for Relational Database Services, with a feature called as multi-AZ deployment. Here is how it works. When you enable multi-AZ, AWS automatically provisions a primary database instance in one availability zone and a standby replica instance in a different availability zone. AWS synchronously replicates every write from the primary to the standby in real time. This is synchronous replication, meaning a write is not confirmed to your application until both primary and secondary have committed it. This gives you zero data loss in the event of a primary failure. Now, a common misconception: the standby is not serving reads, it is purely a failover target. All reads and writes go to the primary, the standby just stays synchronized waiting. If the primary database fails, hardware failure, AZ outage, network issue, AWS detects the failure and automatically promotes the standby to primary. Your application's connection string points to a DNS endpoint that AWS updates. The failover completes in approximately 60 to 120 seconds with no manual intervention. For production systems, this is non-negotiable. No serious production database runs on a single instance. Multi-AZ is about availability. Read replicas are about performance. They are different features of Amazon RDS. So if you want to scale your read traffic, for example, a reporting dashboard hitting the same database, that's where RDS read replicas come in. They are separate from multi-AZ feature and can be in different regions entirely. We will cover read replicas in a future video. Now let's trace the complete journey of a single user request through its architecture from click to response. Step 1. A user opens your application on their browser or a mobile app and sends a request. This hits the public DNS endpoint for your application load balancer. Step 2. The ALB receives the request. It checks its list of healthy EC2 instances across AZ1 and AZ2, selects one using its own routing algorithm and forwards the request there. Step 3. The selected EC2 instance, your application server, receives the request and processes the business logic. It might validate authentication, transform data, and call other services. Step 4. The EC2 instance needs data, so it queries the RDS primary database. The database fetches the records, returns them to EC2, which formats and sends the final response back to the user. The entire round trip, all of these 4 steps, happens in just milliseconds under normal conditions. Now here, let's bring everything together with the key takeaway from today. 1. High availability means eliminating every single point of failure. If your architecture has any component where failure means an outage, it is not truly highly available. 2. AWS Foundation, regions and availability zones, gives you the physical infrastructure to build resilient systems using multiple AZs. 3. The application load balancer is your traffic intelligence layer. It distributes load, performs health check, and ensures users always reach the healthy servers. 4. Auto-scaling makes your architecture both available and economical. It handles demand spikes automatically and scales down to save cost when the traffic drops. 5. Multi-AZ is non-negotiable for production database. Synchronous replication and automatic failover means your data layer is as resilient as your compute layer. Together, these components form a pattern that is standard for production AWS deployments globally. If you understand this architecture, you understand how modern cloud applications are built. That's a wrap on today's video. If this has helped you understand how real AWS architectures are designed, I would genuinely appreciate if you subscribe to Cloud Pathway Academy. I create content specifically for developers and engineers who want to go from AWS beginner to cloud professional. And we have a lot more in-depth videos coming. In the next video, I will walk you through this architecture and help you build in live console. Every service, every configuration, step by step. Drop any questions in the comments below and I'll see you in the next video. Thank you.